We are opening a meeting of the Dissertation Council on the defense of the dissertation of Kavokin Kirill for the degree of Doctor of Physical and Mathematical Sciences in the degree field 040110 Semiconductor Physics on the topic Relaxation of Angular Momentum and Energy in Spin Systems of Semiconductors. By the order of St. Petersburg University, dated March 6, 2020, number 1684/1. I, Vadim Fedeyevich Agikan, Doctor of Physics and Mathematics, Professor of the Department of Solid-State Physics of St. Petersburg University, was appointed Chairman of this Dissertation Council, and the same order approved the members of the Dissertation Council. Allow me to introduce them in accordance to with the order of St. Petersburg State University, dated 23/03/2020. Our meeting is held in the remote access mode, in which my colleagues, members of the councils are, the members of the Dissertation Council, Alok Vivenko, Doctor of Physical and Mathematical Sciences, Professor, Department of Solid-State Electronics, St. Petersburg University. Well, that I already, the 19th of June, 2020, 3 p.m., 15:00. Kolakovsky Vladimir Dmitrievich, Doctor of Physical Mathematical Sciences, Professor, corresponding member of the Russian Academy of Sciences, Principal Researcher of the Institute of Solid-State Physics of the Russian Academy of Sciences. Can you see us? Leonid Evgenievich Golub, Doctor of Physical and Mathematical Sciences, Professor of the Department of the Russian Academy of Sciences, Head of the Department of Institute of Physics and Technology, named after Yoffe of the Russian Academy of Sciences. Tatiana Vasilyevna Shubina, Doctor of Physics and Mathematics, Chief Researcher at the Physio-Technical Institute, named after Yoffe of the Russian Academy of Sciences. Can you hear us? And yes, yes. Mikhail Igorevich Diakonov, Doctor of Physical and Mathematical Sciences, Professor of the University of Montpellier, France. Can you see us and hear us? And the applicant, Kirill Vitalyevich Kavokin. Can you see us? Can you hear us? Yes, yes. All members of the Dissertation Council are online, and the candidate is on. Because since our meeting is held in remote access mode, please follow the procedure, and if a technical failure occurs, you stop seeing or hearing someone, please inform me about this. I will announce the technical break until these problems are resolved. In case the connection with me is interrupted, I will ask the next on the list, Oleg Fedorovich Vivenko, to make a statement about technical break, and in case of failure to restore connection with me, to conduct the meeting further. Do you agree? Yes. Do others have any objections? No. Then we continue our session. Well, please switch off the microphone when you're not online, when we're not given the floor, to improve the quality of communication. Well, I also inform you that the audio video recording of meeting and the live broadcast of the St. Petersburg University and being carried out, and speeches are being interpreted from Russian to English and from English into Russian. The applicant's page currently has an email address at which, during the meeting, all listeners of the live broadcast of the Dissertation Council meeting can express their opinions and questions by email, and these questions will be sent to me by the technical services, and I will voice them during the discussion. Although all those asking questions should assign their with a name, position, and place of work. In accordance with the procedure of awarding academic degrees at St. Petersburg University, of candidate and Doctor of Sciences. And the session is legitimate if at least two-thirds of the approved composition participate in its work, and not fewer than 4 people. Our dissertation council consists of 6 people, or 6 are present, all in a remote interactive mode. Everybody is in contact. Audio-visual contact is provided. So there's a quorum. I entrust the curator of the defense, the specialist of the Department of the Support of the Dissertation Council, Karpova Natalia Vladimirovna. Well, unfortunately, Tatiana Vasilyevna Shubina is not online. Please, I announce a technical break. So, the procedure of today's meeting, a brief report of the chairman on the documents submitted by the applicant for the academic degree and their compliance with the established requirements, answers to possible questions, approximately 5 minutes. A brief report of the applicant for degree reflecting the main points of his research, approximately 20 minutes. Questions to the applicant strictly according to the report, not more than 2 minutes per one question. Answers of the applicant no more than 5 minutes for all questions. Speeches by all members of the Station Council alternately with their assessment of the dissertation research and the applicant's presentation with summary of their positions, approximately 10 minutes per speaker. Speech by the chairman with the assessment, approximately 10 minutes. The final answers of the applicant to the questions asked, no more than 5 minutes. Presentation by the chairman of questions to the applicant that have been submitted by email in order to discuss. Well, we continue. Then open call voting, counting of the votes by the chairman of the Station Council and entering the results into minutes of the meeting, making a decision on awarding or not awarding a degree. The final statement of the applicant. Dear colleagues, if there are any questions or objections to this procedure, then I will proceed. We'll proceed to the implementation of the agenda. Please, before that, I would like you to turn off the sound on your mobile telephones. Therefore, Kirill Vitalyevich Kavokin's dissertation for the degree of Doctor of Physics and Mathematics in the academic degree field 040110 Semiconductor Physics on the topic Relaxation of Angular Momentum and Energy in Spin Systems of Doped Semiconductors was accepted for defense by the order of the Academic Secretary of St. Petersburg University, dated March 6, 2020. Kavokin Kirill Vitalyevich wrote his dissertation research in St. Petersburg University. The number of publications of the applicant in which the main scientific results of the dissertations are presented, according to the presented list, 21 works. In publications indexed in the database Web of Sciences Scopus, 21 publications. In peer-reviewed scientific publications from the list approved by the Ministry of Education and Science of the Experience, there are no publications. The applicant submitted to the Academic Secretary of St. Petersburg University a full package of documents for acceptance for consideration of defense. All documents correspond to clause 12 or section 3 of the procedure. All documents presented by the applicant according to the information I received from the curator comply with the requirements and are stored in the certification file of the applicant, copies of which are available from the member of the Department of the Support of the Station Councils and the curator of today's meeting, Natalia Vladimir Karpova, is now online with us. Before giving the floor to the applicant, do members of the Station Council have general questions or objections? No. Therefore, then would like to give the floor to Kirill Vitalyevich Kavokin. Your floor, Kirill Vitalyevich. Can you all see the presentation? Can you see the full screen? Yes. Yes. Dear colleagues, I would like to present my dissertation work on the relaxation of angular momentum and energy in spin systems of doped semiconductors. The work consists of the introduction, 6 chapters, and conclusions. You can see the name of the titles of the chapters. The scientific context is spin physics and optical spin orientation in semiconductors. well, this phenomenon in electron and in nuclei was conducted by George von Perren, and in two. First of all, as is the transfer of momentum. You see a bulk that is that results in dynamic polarization of nuclear spins, according to Lampel in 1968. And you can see here bulk semiconductor with cubic lattice. Well, the average spin is 0.22. The second one is this dynamic polarization of nuclear spins, which is possible because superfine interaction of in the form of spins in the switch of in the nuclear acquires polarization as a result of this process. So due to these simple facts, physics, a very rich physics was born, but that has been studied for over 15 years. And you see that a monograph was published, Modern Problems in Condensed Matter Sciences, Optical Orientation, and the studies have been done on semiconductor compounds. Third, fifth, and second and sixth groups, you can see on the contents, if you look at the contents of the optical orientation, that there's been a very thorough approach. You can see the chapters that are indicated with arrows directly relate to what I'm presenting today. Full picture has been received about semiconductors. And you would think that optical orientation theory is closed, but when spintronics was announced for technical use of spin semiconductors, researchers found out that some applications of spintronics have very unclear foundations. Unfortunately, there was no evidence that the evidence that was used in spintronics was not included in this monograph because in the third chapter, spin relaxation of under optical orientation of semiconductors, p-type. These are not principal carriers, and there's electron nuclear optical coupling between electronic and nuclear spins. This doesn't exist when light is turned off. And this has to do with the feed-in of energy into the system. And the physics of oriented spins is very understudied and very also low magnetic fields are understudied as well. Well, there's been a big gap in the knowledge field, and to close this gap, uh, we I wrote this dissertation according to the logic of the development, and historically we should start with the main inter interactions between resonant spins and semiconductors. What this is what we know. This is conduction band electron interactions. First of all is Zeeman interaction. So Zeeman energy through magnetic field, and this is a hyperfine interaction that provides the transfer of angular momentum to the nuclear, and the Overhauser field, then the magnetic dipole interaction. Well, and that magnetic was very weak, but what's important is the exchange interaction that has that that's important for local the interaction of localized electrons, and there's not enough knowledge. The two electrons, um, if the if the electrons to the transfer. Sorry, there's a connection lost. Vadim Fedevich, please, technical break. We announced technical break. We continue. We can continue. It stops that the exchange interaction of electrons that belong. Technical break again. Declare. Vadim Fedevich, yes, please. We continue. the exchange interaction of electrons that belong uh, was considered as isotrope because because the spin of electron the electron spin is isotropic, but this is not so because in the zone of conductivity there's spin orbit uh, components that look like as the scalar sum of spin on the electric field and and this is for cubic um, this is for cubic semiconductor. What it leads to the this is for free electrons, and it doesn't and for localized electrons as well. The impulse was false, will be false, and the addition of to gamma the spin turns around the field and with some angle, the two electrons cannot meet uh, with orientation of spins in whether spins are are diverted together and the exchange integrate becomes zero. Electrons must meet, and this circumstance leads to the interaction of effective arguments that I uh, diverted at a certain angle. Well, if you look at the spins from to a laboratory system, this scalar interaction and to other components and this and the last one is and, and connection is lost. The contribution of different components to the exchange interaction is determined by the angle of the rotation of spin, which can be calculated by knowing localized potential and the constants of spin orbital interaction. Well, you can calculate in different ways. And took my work of 2004, there was a unitary transformation method was used. You can see you can remove spin orbital sum. Can we continue? Yes. Kirill is not online. Well, let's see. Technical break again. Technical break is announced again. Suggestions. Yes. The break is over. We continue. Your well, when you the more is the angle, and it's determined by spin orbital constants. The connection is restored. Please continue. But it's missing. Some atmospheric phenomena. When we had the test session, everything was working fine. But yesterday, although there was a thunder and lightning, but the connection was down completely between neighboring houses. Maybe maybe this is the result of a cyclone from too many free electrons, and they're rotating, and it's not possible to The break is over. Now we continue our session. As I said, there's an isotope contribution to the exchange or interaction. As we know, this leads to spin relaxation. We could expect would expect that on donor electrons and n-tip the semiconductors. We've done some experiments to test this. The optical orientation method and Hanley effect was used to here's online again. Then continue. Thank you. There have been measurements of spin relaxation electrons and the correlation time. This is within the fading of the spin in one donor and pressurization recovery. The measurements used a very large band, and we have a picture here from the original work 2002, and you can see three zones of strengthening, tempering. This corresponds to Kavokin Kirill mechanism, and here the time increases. That has to do with the fluctuation of nuclear spins that are more effective than if the time is shorter of correlation, and the more donors, the more exchange, the stronger the exchange. Anisotropic exchange is important here, and there's a decline of spin relaxation that has to do with this new mechanism. It has to do with anisotropic interaction. There are three mechanisms that are described here, and theoretically, only an isotropic exchange needed a new theory. Everything else was known. We had to take account of the scattering of charged impurities. This is depending on the scattering, the correlation mechanism is different. So this scattering is at charged impurities, and This and the vector is determined by Fermi. You can see this the concluding curves, the functional interdependence is described very well by theory. But if we take measured impulse time of relaxation, there's a lack of agreement, and then and this is part of the Dyakonov-Kirill mechanism of spinor relaxation, and there's a lack of agreement with transport measurements. And the cause of this lack of agreement is not known. The same thing happens with higher temperatures, with room temperature, with different levels of temperature. From the transfer measurements and the optical measurements, the values are different. This is a new mechanism of relaxation based on anisotropic exchange. It's very hard to calculate because there's arbitrary position of donor electrons, and the integrals of depend on the distance. There's no exact no Я вроде вошел. Спасибо. Я уже вот пришел. Меня почему-то прервалась связь. The break is over. I will continue the presentation. I started talking about that there is the spin relaxation is limited by the energy, and this is only in circumstance of real jumps, and energy is transferred. The number of such pairs that interact with phonons is not very high. The number of these pairs, this spin relaxation is done by spin diffusion, and the rate of relaxation is described by the Hussashi-Dejean theory, and it turns out that experiments done by Vasily Belich show that this mechanism exists, and with the growth of magnetic field, the diffusion rate is slowing down. So, and this can be seen by the width of lines of spin dumps. The time of relaxation is growing this way, and it's in agreement with this model, with the since recollection is done this way. There are a lot of spins of electrons in the lattice, and the interaction is faster than the equilibrium is achieved in the lattice. Therefore, we can assume that the initial relaxation electron spin dynamics will be described in longitudinal magnetic field. And there will be the first relaxation is of non-equilibrium electron spin, and then relaxation of Vasily Belich made this experiment again with some range of concentration. He saw exponential dynamics. Good theoretical hypothesis was proved, and this is part of the statement of the defense. The nuclei with some dynamic polarization, and the field, Overhauser field, is very varied. Well, depending on whether there's an electron or there isn't an electron there. If there, they have angular spins, then there's a recession of such electron spin and or in spin noise. As I said, the aim of this work is to investigate spin lattice relaxation of nuclei. Therefore, we had to use special methods that don't stir up the spin system, a nuclei system. Some methods were devised in this work. Two of them had to do with micro resonators, where Faraday rotation when photons of light go through the resonator, that leads to an effect that was predicted by years ago. The electrons are not needed that lead to Faraday rotation. You see here experimental pictures of this Faraday rotation. And after this time-dependent Faraday rotation induced by electron and nuclear spin polarization, this nuclear spins the different components with different times of relaxation, up to a fraction of a second to several seconds, and you can see curves for semiconductors with free electrons, and the time here is of up to 10 seconds to confirm that these two components have to do with nuclei. There were resonance experiments conducted. Then the nature of these components, you see that the long-living component is has to do with Oberhauser field, and the shorter lived is the dielectric material in donors, in clusters of donors, pairs or three clusters, three component clusters. There are different signs of the two components in metallic phase because there are two origins. The different edges. Long-lived is the splitting of zones, and the short-lived is based on the blockades. And so this effect was seen for the first time experimentally, and so it was put in the statement, definitive statement number 4. Another method that we used, which was used for the first time, is the measurement of Oberhauser field electron spin noise spectroscopy measures time-dependent Overhauser field. That was done by Zapaskin and was used to assess HEM semiconductors, but we used a resonator. After we pumped nuclear, you see this spin relaxation of nuclear. You see this curve when that's two, the external field and the Overhauser field are summed up, and this is when they deducted. And to expand the class of structures, we used a long-served methods of polarized photoluminescence to after pumping, the light was switched off and the nuclear relaxed, and after they were pumped up, then polarization was detected, and this reflects the difference of Hanley effect in the Overhausen field, because the nuclear relax more and more during the time when this light is switched off. When I already said it, the spin system is well isolated from the lattice, and this is well described by steam temperature, by Purcell and Pound, and experimentally also first optical pumping semiconductors was described by Dyakonov and Kirill. The theory provides that in the spin system of nuclei, there's complete equilibrium at a certain spin temperature, and the Curie law is used to assess the magneticism of the spin system. The adiabatic remagnetization of nuclear spins, predictions of spin temperature theory at large values. Spin. It leads to the changes in spin temperature because of the changes in Zeeman reservoir temperature. The registration of this curve of adiabatic remagnetization is a way to check that the spin temperature theory is right, because it all depends on the splitting of spins, and it has to do with resonators and heterostructures. So the splitting is we think is there. An experiment of direct proving of spin temperature theory has been done by us for the first time, and nobody has done it before. You can see the results of adiabatic remagnetization by Faraday rotation. When you scan the paramagnetic field, the nuclear don't relax very much during this time. This trend it has to do with the influence of the external field. And so as a result, this is the curve of remagnetization. The magnetization of nuclear is described very well by the temperature theory, with one exception. That's the local field of dipole-dipole interaction is different from the theoretical values. The same is detected for spin noise. That's why we have to take into account spin lattice relaxation, but the result is the same. The spin system is well described by the temperature theory, but the local field is not the same. Well, we think that the quadrupole splitting is another factor that influences this process. Well, the splitting is stronger than dipole-dipole interaction. The system comes to an equilibrium. But we can think in different ways how this happens. There are many isotopes with each with its own constants. Well, the distance between different levels is not that large. The spin temperature is very stable. In all structures it works, but you have to know what local field there is there. And then the mixing of Zeeman and spin-spin reservoirs with a higher value of the external magnetic field and the high splitting. The Zeeman reservoir is very much detached for spin reservoirs, and what comes out is the mixing field. In our experiments, we tried to find this moment of mixing that could lead to the change of the curves of remagnetization, but nothing of this thing happened up to the 50 Gauss field. the dipole-dipole interaction is very weak. And we continue. We'll find out. Wait a moment. Can you hear us? Everything is okay? Kirill, please continue. You have two statements for defense. Which I just wanted to talk about spin lattice relaxation of nuclear. As for electrons, even more than depending on the magnetic field, and it consists of energy relaxation and the angular relaxation in the strong field and the low field and the weak field. The rate of relaxation is by warming up of the spin system. These processes that are larger than the local field. We just tested that experimentally. We found some regimes of spin relaxation. One is for fluctuating angular momentum relaxation. There are some deviations. The semiconductor is not perfect and type nuclear spinless relaxation metallic JS occurring mechanism was used there. Nuclear spin lattice relaxation and dielectric and and this is diffusion limited relaxation is described by Dijon Kutishvili theory. This is in the weak magnetic field, the relaxation takes the root, is developing faster, much faster. It's hard to explain than in the stronger field because it has nothing to do with nuclear close to donor system. You can see here that the measurement of several hundreds of milliseconds, the time of relaxation of this nuclei is determined by diffusion. The only the electric fields are ignite. You see that this magnetic field is activation and capture is by charge hopping and spin exchange. You can see this. This is how you can describe this warming up effect. This has to do with the temperature is determined when the temperature of the field is determined by Zeeman reservoir. It describes the defender statement number 6, or is described by the defender statement as M6. You see spin lattice relaxation nuclei and the gas type semiconductors can occur by the mechanism of warm-up of the nuclear spin system by fluctuating electric field arising from thermally activated carrier hopping. And the whole relaxation here takes only some milliseconds. This is a mystery because the holes interact. The interaction of holes with nuclei is much weaker. The nuclei are polarized by and this contradiction can be resolved if we use Benjamin and Korb 2008 result, who saw that when of the capture of the electron on donor center, there's a big fluctuation leading to the warming up of nuclei. The quadruple there's a radius, the spin lattice relaxation nuclear in p-doped GAS type semiconductors after their optical pumping occurs 3 orders of magnitude faster than in N-type semiconductors as a result of fluctuation in the charge state of donor receptor pairs. The relaxation is based on quadruple interaction. That's near the charged donor. There will be the charged acceptor, and the hopping of this charge from one acceptor to the next leads to the fluctuation of electric field. If we look at the function of scattering, we can describe the values and the temperature dependence of the spin lattice relaxation. So this is included in the 7th statement to be defended, and only conclusions remain to be made, which I formulated in a very laconic way. In the dissertation, there are 2 pages devoted to. We can see the results. I will not repeat them. And there's the list of publications containing 21 journal articles and monographs. Thank you very much. Members of the Station Council, do we have any questions? Do you have any questions on the presentation? I have one question. Can you show slide number 10? You showed this picture. I cannot hear you. I cannot collect further. The connection is lost again. Can we declare a technical break again? Technical break, yes, yes. All these centers are filled with electrons. There's one empty. You said in your words that they're filled with electrons, and they interact, exchange. Are there any free spaces where they can go? There's a compensation always. Well, the level of compensation is not high. Then the number of empty charged donors is smaller than filled donors. If we take $1 for most donors, it's just spin exchange. Well, this is the statement. If we look at characteristic times of relaxation, there's a correlation, and account for hopping times with Gilliam. The spin exchange is not dependent on temperature. Fedors, do you agree with do you accept the answer? Any other questions? Can you see us? I have a very naive question, Kirill Vitarovich, about the times of spins and diffusions and the parameters associated with it. The width of zones of the energetic zone can affect these. The energetic width of the impurity band. If we change the place of two electrons, the charge value won't change. Well, if we apply a magnetic field, the Zeeman energies will be different. This is the reason why and belief experiment. There's this disagreement of are there any questions from other the degree of compensation? Do you have any figures for that? On these samples, we couldn't measure probably 10% the characteristic value. Any other questions on other? If there are no questions, then we continue to the reviews. The reviews have been published on the websites. Therefore, just maybe critical comments and questions should be voiced. Therefore, Fedor Shkrivenko, you will be the first to read your review. Do we have any problems with the connection? Your review, please. The main moments. Well, it's a short review. One. That's well, the dependence of time on spin relaxation. The new methods of the new methods of non-disturbed control of magnetized nuclear spin system as proposed. And there's the dissertation also provides new data on the mechanism of spin lattice relaxation of previously optically cooled nuclear and semiconductor structures on the basis of arsenide gallium and weaker magnetic fields with the absence of optical stirring. And I think that they work well some critical points, and the crystals chairs with the concentration of donors of higher than 2 by 10 and to the magnitude of 16 centimeter cubic minus cubic centimeter are called metallic. At the same time, the characteristics of the conductivity at this level of tempering are far from a good metal. And also on page in figure 4.3, there's a typo. And the third chapter, there's a disagreement of the times of relaxation of impulse scattering that were received through transport measurements and from the subduing of spin relaxation by longitudinal field. Well, unfortunately, this was not described in detail, and nevertheless, on the whole, I think that the dissertation of Kirill Vitalyevich Kavokin totally complies with the requirements of the regulations on awarding the degrees, academic degrees of St. Petersburg University. I would like you to answer the question. The first is about metallic. It's the terminology question really. To remark, the adjective metal was used due to lack of more exact term. This refers to crystals and structures on which at low temperatures delocalized electrons in the conduction band. However, at such concentration, of course, there are localized electronic states, which was manifested among other things in our experiments. Then the adjective metallic is quite conditional. Well, almost metallic. As far as figure 4.3, now it's a typo thing. So as far as the mismatch in the chapter 3, the only are not clear. The reasons for this mismatch, unfortunately, are not clear. The only one discussed in the literature, the mechanism that can lead to this behavior is electron scattering, which is not affected by conductivity, but doesn't affect the conductivity, but affects the spin relaxation by the Diakonov-Perel mechanism. However, a study of this phenomenon by Glazov and Ivchenko and Theory and Harley in an experiment showed that electron scattering significantly affects spin relaxation only in quantum pits with electron gas, and even there, only at sufficiently high temperatures and bulk materials, its role is negligible. The data on spin flip scattering were used precisely for the reason that in these experiments a comparison with conductivity is used, and spin splitting is directly measured for a given wave vector, which directly gives a spin orbit constant. Here also possible errors, since the experiments were performed not on bulk crystals but on quantum dimensional structures, but still these data seem more reliable. Well, the they they the experiments and the experiments include recalculating of constants. It was not possible to draw. Oleg Fedorovich, do you agree with the no? Do you accept the answers? Yeah, we need to investigate this further. Thank you very much. Vladimir Dmitrievich Kolakovsky, your review. I won't read my review in full. What was done in the dissertation is huge work, and I have to point out that this isotope scattering was discussed in such detail, but there's a link between Kirill with other experimental scientists. Not only theoretical works have been reviewed here, but of warming up the system that have never been used and that we use here. So relevant and unique. Some questions, of course. What we the high value of the local field and the gap resonator is linked to the deformation of this layer, and therefore the required value of which approximately 0.01% is quite possible, and therefore maybe it would be advisable to additionally measure this the value of the field of mixing B-mix and compare it with the calculated value taking into account the quadruple splitting of nuclear spinning levels in the gaseous layer. Also, the temperature dependence between the time of spin lattice to relaxation T1 in the p-type that's represented in figure 6.4b demonstrate a very dramatic growth when the temperature declines below approximately 6K, and that's the location of which is not dependent on the magnetic field and the concentration of acceptors. And then and of course there are some stylistic comments. In 6th chapter, a lot of experimental curves for different samples with different structures as provided in the first paragraph, while their discussion in the subsequent two paragraphs, and it's hard to read the text if it's laid out this way. Um, but all the statements to be defended are valid and are proved, and therefore the dissertation of Kirill Kavokin on the topic of the relaxation of angular momentum energy and spin systems of doped semiconductors uh, completely conforms to the requirements of St. Petersburg University on awarding doctoral degrees. Please answer the questions. As far as the mixing, see the shape. The field of mixing is manifested in the deviation of curves of magnetization from adiabatic. The more the field is closer to the local field, the curves are closer. Well, unfortunately, we cannot calculate even better. Well, so it can be seen the deviation of the curve magnetization of nuclear from adiabatic is very slight, and the moment of mixing of the tanks hard to fix. As far as the second question, most likely the roughness of the model, which takes into account only the hopping between the two nearest acceptors, does not take into account the spread of distances to them. The distance to these centers are taken equal to the maximum corresponding distribution functions. As far as the layout, try to make the presentation more logical, concentrating on the experimental results at the beginning so that when reading the theory, there are no longer new things, but perhaps this is not the best option. As far as the figure, there's a typo, of course. As for my correspondence with the experimenters, I received most experimental results from my own experiments, either by sitting at the equipment or discussing what's received by those who were there. Then now limit. I have all the necessary points, the relevance and the significance. I will skip in my review. They're there, and then I recount what I understood from the dissertation. Well, no need to read all this. I just wanted to point out to one thing, that we are witnessing a defense, a very unique defense of a scientist who can publish theoretical papers, but also conduct experiments independently and invent something. Well, there aren't many scientists that would be experimenters and theoreticians in all in one. And colleague Kavokin is is sometimes known as the experiment or some as a theoretician, but people just are amazed that we deal with both in one person. That three three comments that I put in my review. First one is what well the answer to the question is the chapter 2 that the spin orbit field is proportional and this that's the answer to the question is no. The question is that for the simple case when spin orbit field is proportional, when the components of the wave vector has stable spiral structure as persistent spiral helix. The second question, when we see the cubic symmetry of the crystal, it's possible to remove the spin dilution, and there were such works and when you discuss experiments that that deal with the systems of high exchange interaction, this fact is not taken into account. Yes, I'm answering. The first one. The first question has a clear answer. First one, anisotropic cubic components, and then diffused system of well, the question to this question is known only for the simple case when the spin orbit field is proportional and one of the components of the wave vector then stable spiral structures. But such situation is realized only in specific two-dimensional structures, for example, in quantum holes with the orientation of 110. For the general case, the answer, as far as I know, was not found. Therefore, in order to theoretically describe the dynamics of the full spin in a microscopic system, one has to resort to non-strict methods, such as the approach developed in this work, using the concept of spin diffusion over an infinite cluster. Nevertheless, one can hope that it correctly reflects physics, disordered spin systems of localized electrons. As far as the second question, the contribution can, these works that were cited can have appeared after 2008, and well, fortunately, the sound is lost. Technical break is announced. The break is over, please. As I said, this contribution can manifest itself in highly diluted systems when spin diffusion is weak and becomes and relaxation of the clusters closest space donors is there. In the dissertation, this mode is not discussed in detail. It is analyzed in the original work uh, when in where just in my paper, it's concluded that triples can, with the removal, an additional contribution of pairs of donors appears. In the experiment of on-CAS in the limit of weak doping, relaxation on nuclei dominates. Therefore, the removal of spin to in pairs is not showing up. As far as the other question, the the sketchers the thank you. Do you accept the answers? Tatiana Vatina Shubina, please. Yeah. I will not give you a characteristic of a general characteristic of the work. Technical break is announced. The break is no, not ready. I'm the technical break is over. The, well, my opinion about the work, that is a wonderful work. With some corrections, it would be a very good monograph, wonderful monograph on the topic of spins in semiconductors. And we haven't had many recent works devoted to this stuff. And after this, I will turn to the drawbacks. There aren't many. Some comments. The method of spin noises is treated as no stirring, but it's known that the mechanism of emergence of the signal of spin noise is analogous to the mechanism of combined scattering of light with the turnover of spin, and therefore the light, the ray of light can lead to the changes of spin state. Well, and the second one is microresonators. So the amplitude of optical field is increased. Can it impact the spin dynamics in such structures? In this station, the constraints on the power and the polarization of the polarized probe beam as are not discussed. The third one is that in chapter 3, the author analyzed mechanism of spin relaxations, and with the transfer of dielectric metal transfer, but the area of this transfer is not discussed. Yeah, all the rest, I support the decision to award a third degree. Yes, please answer the questions. As far as the first spin noise, there's constraint of this kind. Quantum constraints are important when measuring the state of a single spin or a small number, because we cannot find the volume of the probed region. In our sessions, typically the volume of the probed region was of the order of 10 to 10 centimeter and 3 minus 3 magnitude, and which at an actual concentration you can see 10 to 6 by 16 centimeters minus 3. It gives the punctuation of the order of 1000 spins. Therefore, the measured noise Faraday rotation was classic, and the quantum effects, which include change the quantum effect to which the changes in spin states of the ensemble of electrons through spin flip scattering were not large, due to were not significant with some intensity of the probe beam that are adequate for, that would be enough for registration of signal. As far as the second micro-resonator, yes, it does. Now, work dynamic polarization nuclei was observed the elliptically polarized glow beam, as well as the appearance of an effective optical field acting on electronic backs through the inverse Faraday effect. To avoid this, I had to orient plane of polarization of the probe beam so that the linear polarization is not converted into elliptic due to the internal anisotropy of the micro-resonator, and to reduce passing through resonator power up to values of the order of microwatts. As far as the third question, there is no constant theory of spin dynamics of in the metal insulator transition region. At the same time, approaches that are valid in the dielectric and metal fields are well extrapolated in the vicinity of the transition region, so that the region not described by the theory is rather narrow. The scatter of experimental data does not allow us to state anything definitive regarding the concentration dependence of the spin realization time in this region. The observed gap is due to the rather a change of in the spin orbit realization mechanism from anisotropic exchange to the Dyakonov parallel mechanism, then rather than directly by the physics of the transition region. Note that on a series of heterostructures studied in the Luhmann and et al., the gap is not visible at all, which is apparently due to a shift in the spin-time relations in the dielectric phase due to the depletion of active layers of structures. Such a discussion should be, of course, be included in the text of the dissertation and will be good for further research. And now, like to turn to Professor Dyakonov. Can we see him? Mikhail Igorevich, your review, please. Well, my review is uploaded. The first thing I wanted to say, this dissertation could have been defended 10 years ago or even earlier. Kirill Vitalyevich is a wonderful specialist in this field who has contributed a lot as an experimenter and a theoretician, which is a unique combination in this age day and age. And I don't know anyone else who could be equally versed at this semiconductor spin systems and what happened to semiconductors in relaxation, etc. Well, he's a master in this field. But what else? At the initial stage of the development of this area in the 80s and the 1980s, this was a period of storm and drunk period. There were very new. There was a spread of new phenomena discovered that people didn't know what to investigate first, and this period is over now. And now there's another period of serious work with attention to detail, how things are compared to each other. And Kirill did all this. and wrote it up with thoroughness, with close attention to detail. I think that this is an exceptionally good work, and he has been deserving it, deserving a Doctor of Sciences degree. I have no drawbacks. I could, of course, find, but I don't think there's no need. I think there's no need. So no questions, no answers. This is then my review is the last review. This research started about 50 years ago. Mikhailovich and Vladimir walked the corridors and created the science. This became so wide that it still remains this way. Kirill Vitalyevich is an experimenter because I looked at him emptying helium from one reservoir into small vessels, and his postgraduate has recently defended his dissertation, well prepared, and Kirill Vitalyevich joined the university quite recently, a laboratory that was created, financed by a mega grant several years ago, received by the university several years ago. As far as the drawbacks, the dissertation talks about a huge role of quadrupole mechanism in of spin lattice relaxation. Maybe you should have talked more about maybe how the quadrupole splitting is affected by the splitting of anisotropic splitting and the sign of deformation, the compression and the stretching of the active layer, and second is the metallic in the metallic JAS because as a result of the study of the relaxing momentum, it's the author says that there's a huge role of the interaction of nuclei with electrons localized on donor pairs. Is it valid would it be valid to isolate separate donor pairs in the crystal with high concentration of donors? And also there's a correlation, uses the term so-called time of correlation, but doesn't explain this term. The work has a lot of legend symbols, and there's a list of such designations that could, of course, facilitate the reader in the station. But my conclusion is that Kirill Vitalyevich Kavokin deserves being awarded an academic degree of Doctor of Physical Mathematical Sciences. The first question is a bit anisopy. I agree that this should be discussed. The answer as of the quadrupole of the quadrupole splitting, the answer is simple. In the investigated case of weak magnetic fields, static quadrupole splitting affects the relaxation rate only in terms of the effective local field, which is proportional to the mean square of the quadrupole energy and doesn't depend on the sign of anisotropy of the deformation. And there's a work now being defended by postgraduates in Germany that who deals with this. Yes, there is a relaxation and there's deformation. This affects, but I don't know how it affects so far. Second, about the pairs. Two things here. The localization on clusters of all sizes plays a role. However, the donor concentrations couples still dominate. For example, the concentration of triples is estimated the concentration pairs multiplied by the probability of another donor falling within the shielding radius. So the contribution of triples is not that significant. As far as the definition of correlation time, I already mentioned it in my presentation. This is the average decay time. Correlation function of electron spins localized in the arbitrary donor. I agree with the absence of the list. When you write your monograph, please make this list. Yes, if I do, I will do that. There are no external reviews to the dissertation. On the dissertation. Natalia Ledger, no external reviews. No. As far as comments or questions from listeners, no questions have arrived at the electronic email address. Therefore, we have a possibility to turn off the sound and discuss the resolution to award a degree if it's needed. If members of the station don't feel that there's such a need. Do you have any objections to drop this? Yes. No. Therefore, we continue with the voting. I would like to ask each one of you, Vivianka, Oleg Fedorovich, your opinion in favor of awarding the degree. Kolakovsky, I am in favor of the awarding of the Golub Leonid Evgenievich for the awarding of the degree. Shubina Tatiana Vasilyevna. Shubin. Your opinion, for or against? You vote for or against? I cannot hear you. Yes, we are declaring a break. But technical break. Yeah. Is the break over? Technical break declared. Announced. Good. As far as I understand, there was a we're finishing our technical break. We're returning to Tatiana Vasylievna. I agree. I'm say yes to the awarding of the degree. I Gakan Vadim Federation, I am in favor of the degree, of the awarding of. Therefore, 5 members have voted, and all 5 members have voted for to 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 award Kavokin Kirill Vitalyevich the degree of Doctor of Physics and Mathematics in the academic degree field 04110, semiconductor physics, and this is taken. Dear colleagues, due to the fact that our meeting was held in remote access mode, do the members of the station council or the applicant or other attendees questions, have questions, comments on the meeting procedure? Get an answer for everyone. I would like to get an answer from everyone. No. No. Thank you. Kirill Vitalyevich, you have the floor for a concluding statement. Finally, we've overcome all these difficulties. In my concluding word, I would like to thank everyone. It's hard to thank those whom I don't see. I would like to start with those present. I would like to thank the 6 highly esteemed members that I respect so much for reading my research, and for the technical group, Natalia Vladimirovna, who fought through the difficulties we're facing, and also when we talk about those who are not present, I would like to thank all my co-workers in the research that led to the conclusion today, and not only those who participate in this work, but with everybody. I worked with Exeter, Montpellier, Toulouse, and Physical Technical Institute, and Ruslan Ivanovich Choyev has taught me experimental physics. Great thanks to him. And I would like to thank Professor Merkulov, who passed away 6 years ago, who taught me theoretical physics, and also my other teacher in the 90s and the 80s, Professor Jakanov, formed me as a physicist, the seminars that he conducted. Thank you very much. And I would like to thank the people with whom I discussed physical questions. Physics is an oral science. Dima Yakovlev, Ruslan Ivanovich, Alexei Kudinov, my brother Alexei Kavokin, and Masha Vladimirova. Masha Vladimirovna, great thanks to her for the technical help and writing up the dissertation. Thank you very much. Thank you. And thank you, Kirill Vitalyevich. Congratulations on the successful defense. This session is therefore closed. Thank you very much. Turn off the live stream of the meeting. Thank you.